Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 15, 2025, so just about 3 days ago. This paper introduces a new method that can reduce a model's object hallucination rate by a massive 70%, from 15.05% down to 4.53%. The paper is titled, Controlling Multimodal LLMs via Reward-Guided Decoding. And as we'll see, this gives users incredible on-the-fly control over model behavior. It achieves this by using two specialized reward models to guide the model's output, letting users trade off between object precision and recall. Alright, so this diagram provides a great visual for how the multimodal reward-guided decoding method actually works. It starts with an image and a prompt, which are fed to the multimodal LLM. The model then generates several candidate sentences. Next, each candidate is scored by two specialized reward models, RHAL for object hallucination and RREC for object recall. The sentence with the highest combined score gets selected, and the process repeats to build out the full description until an EOS token is generated. Okay, moving to the results. This table compares their multimodal reward-guided decoding method against other approaches on the COCO and AMBER benchmarks. The key metrics are hallucination rates, where lower numbers are better, and object recall, where higher is better. If we look at the baseline LLA-VA 1.5, it has an instance-level hallucination rate of 15.05, but with guidance prioritizing precision, that rate drops dramatically to just 4.53. As the guidance weight changes, you can see the smooth trade-off between reducing hallucinations and increasing object recall, which really showcases the control this method provides. Building on that, these plots show the trade-off between visual grounding and compute. The x-axis, K, represents the number of candidate sentences sampled, while the different colored lines show T, the evaluation period, or how often the reward models are checked. Looking at the two graphs on the left, for precision, we see that a larger K and a smaller T, which means more compute, lead to a lower hallucination rate. The same pattern holds for the two graphs on the right, which show that more compute also improves object recall. This figure then illustrates the precision recall trade-off directly. On the y-axis, we have the hallucination rate, where lower is better, and on the x-axis is recall, where higher is better. The dashed red line represents the ideal curve. You can see how setting the guidance strength W to 1.0 results in very low hallucination but also lower recall. In contrast, setting W to 0.0 pushes recall much higher but at the cost of more hallucinations. And notice how the standard greedy search sits far above these controlled curves, showing a much worse performance. So, wrapping up our look at this work, the main takeaway is the powerful, on-the-fly control this method gives users. By adjusting a single guidance weight, you can smoothly navigate the trade-off between minimizing hallucinations and maximizing object recall, tailoring the model's output for any task. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.